A'udhu billahi minash shaitanir rajeem. Bismillahir rahmanir rahim. My dear student, assalamu alaikum. This is our 13th lecture on advanced stereochemistry. This is our 13th lecture on advanced stereochemistry. Today our topic is Racemisation. It is very important topic for the students of organic specialization, because when you are doing some work on organic synthesis, even if you are doing some isolation, usually during these methods, procedures, racemization occurs. That is why the understanding of racemization is very important, and today we will discuss about the racemization. Only we will discuss the racemization. In our next lecture we will discuss its resolutions, because this is a it means racemization is a problems in the organic chemistry. Then its solution will be required. Its solution is called racemic modification, resolution of racemic
Today's
modification.
key concepts of the lectures are what is racemization and what are the methods of racemization. These are the only two concepts or key concepts of today's lectures, in which we will discuss about the racemization, and then we will discuss the methods of racemizations. Let's start. What is racemization? Racemization is the process. First you understand that what is racemization. From the beginning it starts with very clarity that racemization is the process. It is a process when the enantiomer is converted into racemic modification. Means when enantiomers get converted into racemic modification, that is a chemical reaction. Or when one pure form of an enantiomer is converted into equal proportion of both enantiomers, forming a racemate. When equal proportion of both the enantiomers are formed during the course of chemical reaction and a racemate is formed, and this process is called racemization. Furthermore, resolution is the process. Next is the solution. It is telling about the solution of racemization. It is the resolution is the process when a racemic modification is separated into its constituent enantiomers. Resolution is a process when a racemic modification is separated into its constitutional enantiomers. This is called resolution. Racemization is a thermodynamically favorable process. This is the point to understand. There are two processes. One is kinetic control and other is thermodynamic control. In the case of racemization, this is a thermodynamically favorable process, and it proceeds spontaneously if a convenient pathway is available for the interconversion of enantiomers. Racemization is a thermodynamically favorable process, and it proceeds spontaneously if a convenient pathway is available for the interconversion of enantiomers. It is a reversible process because Any mechanism of racemization must operate from either of the enantiomers. It is a reversible process because any mechanism of racemization must operate from either of the enantiomers. This is very important point. Means the process of racemization is a reversible process because any mechanism of racemization must operate from either of the enantiomers. Furthermore, if a molecule contains more than one chiral center, because sometimes compounds contains more than one chiral center, if a molecule contains more than one chiral center and configurational inversion take place at one center, the product formed is a diastereomers, that is epimer. The process is called epimerization. What is epimerization? Here is the definition of epimerization. If a molecule contains more than one chiral center and configurational inversion takes place at one center, the product form is a diastereomer, that is epimer. From this you have to understand clearly that epimers are diastereomers. Epimers are not enantiomers. Epimers because for it is a necessary condition for the diastereomers that it contains more than one chiral center. It contains more than one chiral center, but in enantiomers only one chiral center is important, and in case of enantiomers epimerization process is not possible. Epimerization is only possible in case of if the compound contains more than one chiral center. The product formed is a diastereomer, that is the epimer. The process is called epimerization. Due to free energy difference, the two epimers exist in unequal amounts in equilibrium. Due to free energy difference, the two epimers exist in unequal amount in equilibrium. Racemization is usually monitored by observing the gradual zeroing of optical rotation, and then from carbon 13 NMR spectroscopy also gives a good probe for monitoring epimerization of both optically active and inactive stereoisomers. Means racemization is usually monitored by observing the gradual zeroing of optical rotation. Carbon 13 NMR also gives a good probe for monitoring epimerization of both optically active and inactive stereoisomers. Now the mechanism involving racemization. What are the methods, what are the mechanisms which are involved in the formation of racemate? First is mechanism involving carbanions. If a ligand at a tetrahedral chiral center is removed by heterolytic cleavage, leaving behind an enanic species, the latter undergoes rapid inversion so that when the ligand recombines, an acidic proton is removed. Using mild to strong bases such as sodium hydroxide and sodium alkoxide. This is the example in which carbanion is formed. You can see that this is the OH, this is the base. It will abstract the most acidic proton. This proton will be abstracted and result in the formation of carbanion, and this carbanion exists in equilibrium. There is a possibility of formation of two product, means nucleophile can attack from front side and from the back side and result in the formation of racemate. This is phenyl S-butyl ketone, and other is mandelic acid. Here OH, you can see this is the most acidic proton which will be abstracted by the OH, and result in the formation of carbanions. These carbanions result in the formation of racemate, mean because there is two two isomers are at equilibrium. When there is dynamic equilibrium, we represent it with double-headed arrow. Double-headed arrow means this is the dynamic equilibrium which is established between the two stages. Here this is the carbanion and this is the enolate form. This is the enol form. These exist in equilibrium. These are two examples in which carbanion is formed, and this carbanion result in the formation of racemate. When the conserved proton is very acidic, as in disulphone, the carbanion may form in appropriate solvents without any base, and the racemization take place spontaneously. This is the example. He is saying that when the concerned proton is very acidic, means this proton, because it is attached with the most electronegative group. Usually those protons are more acidic which are attached with the most electronegative element. That is why the carbanion may form in appropriate solvents without any base, and the racemization takes place spontaneously. Here there is no need of solvents. Sometimes solvents are required for racemization. Here simply in water you can see this proton obstructed and result formation of carbanion. Then there is a mineral acid also affect racemization of a ketone containing an alpha hydrogen. Mineral acid also affect racemization of a ketone containing an alpha proton. This is the structure in which protonation occur, and this protonation result in the formation of carbanions when this bond shift toward this carbanion is formed. These are different methods in which are involved in the formation of racemate through carbanion. Then there is mechanism involving carbonium. There are two carbanion contain negative charge and carbonium and contains positive charge. Electron withdrawing group may be detached from a chiral center with an electron pair leaving behind a cationic species. Racemization occurs when the substrate is capable of giving rise to a stable carbocation. Racemization occurs when the substrate is capable of giving rise to a stable carbocation. This is the mechanism. You can see over there that this is a compound which is going to react with SbCl5, and here carbocation is formed, this carbonium, because this chlorides go over there, and again and there is a chance of formation of racemization because two possible product are possible, one with alpha, one with beta, because this is the pro-chiral carbon, this is the chiral center. If there is change in chiral center, any ligand which is going to change in the inversion of configuration, then there is possibility of formation of isomers. This is R1, R2, R3CH plus H2SO4. Again this is carbocation, and this carbocation when react with this, it results in the formation of racemate. This is the method which involved in carbonium. Here electron withdrawing group may detach from a chiral center with an electron pair leaving behind a cationic species. Racemization occurs when the substrate is capable of giving rise to a stable carbocation. Mechanism involving free radicals. Free radicals having a near planar structure, and if a chiral center is converted into free radical pair by homolytic cleavage of a bond, the recombination of pair leads to racemic product. The examples include benzylic, allylic, tertiary stable radicals undergo racemization under the influence of heat or light. Free radicals having a near planar structure, and if a chiral center is converted into free radical pair by homolytic cleavage of the bond, the recombination of the pair leads to racemic product. Benzylic, allylic, tertiary stable radicals undergo racemization under the influence of heat or light. This is a third method for the uh, racemization for the formation of racemate. When mechanism involving stable symmetrical intermediate, enantiomers are interconverted to stable achiral intermediates and get racemized. This is the fourth method, mechanism involving stable symmetrical intermediate. Enantiomers are interconverted through stable achiral intermediates and get racemized. Example, secondary alcohol in the form of its aluminum derivative heated with ketone, reversible oxidation reduction done, and an equilibrium established between enantiomer or diasteriomer. This is the examples in which a symmetrical intermediate is involved for the formation of a racemate. Here is the example of secondary alcohol in the form of its aluminum derivatives heated with ketone, reversible oxidation reduction done, and an equilibrium is established between enantiomers or diastereoisomers. Here is the secondary alcohol, and here is a ketone, dimethyl ketone. This acetone is going to be converted into a racemic mixture. Here M means dialkyl oxyaluminum, because the reaction of this secondary alcohol with this acetone result in the formation of a racemate. 50% one and 50% other enantiomer is possible. Acid chloride of an optically active carboxylic acid. Acid chloride of an optically active carboxylic acid in the presence of tertiamine undergoes racemization through a ketone. Acid chloride of an optically active carboxylic acid in the presence of tertiamines undergo racemization through a ketone. This is the example. This is the acid chloride. It undergoes, this is the triethylamine, and this is isocyanate and hydrolysis. There is formation of plus minus carboxylic acid. Acid chloride of an optically active carboxylic acid. This is the example of formation of racemate. Plus minus means this is racemate. Then there is racemization through rotation around a bonds. Sometimes racemization occur when the bond is rotated. Racemization takes place through rotation around a single bond or bonds, and the interconversion usually takes place rapidly via an achiral conformation. Most of these enantiomeric atropisomers racemizes by application of heat, leads to bond stretching or bond behind, and helps the nonpolar enantiomers to cross the planar transition state. Cyclic compounds which exist in enantiomeric conformations undergo racemization through ring inversion. Cyclic compounds which exist in enantiomeric conformation undergo racemization through ring inversion. Example, cis-1,2-dimethyl cyclohexane and cis-decalene as the example. Sometimes rotation around the single bond or bonds result in the interconversion and usually takes place readily via an achiral conformation. Most of these enantiomeric atropisomers, when there is a restricted rotation around a single bond, this is called atropisomerism. Most of these enantiomeric atropisomer racemizes by the application of heat leads to bond stretching or bond behind, and helps the non-polar enantiomers to cross the planar transition state. Cyclic compounds which exist in enantiomeric conformation undergo racemization through ring inversion. Example, cis-1,2-dimethyl cyclohexane and cis-decalene. This is the compounds in which racemization through rotation around single bond is occur. When you rotate the bond over here, you will get one enantiomers, and when you will rotate the bond over here, you will get other enantiomer. In the above structural features, that is biphenyl derivatives plus methyl, manous methyl, 2,6,2-6- tetranitro biphenyls, 4,4-dicarboxylate prepared by Misro and Bolstad. These were the scientists who prepared this compound. This is the dicarboxylate, and here in this structure you can see that from here, if you rotate the bond, you will get enantiomers, and here you will rotate the bond, you will get other enantiomers. Both when you after rotation, you will get a racemization. How you will observe the rotation, observe the racemization? Racemization can be observed through polarimeter and through carbon 13 NMR spectroscopy, because by zeroing the specific rotation, it can be easily observed that either a racemate is present or not present. This is another method in which by the bond rotation we can also determine the formation of racemate. Then there is configurational change in substitution reaction. Sometimes there are substitution reactions like SN2 and SN1 reactions. Thus, there is a configurational changes during the course of reaction. In SN2 reaction, the reaction of optically active 2-iodooctane with sodium iodide, the reaction becomes reversible and an equilibrium between the two enantiomers leading to racemization. This is SN2. Here you can see that in SN2 the reaction occur in one step in a concerted manner. A transition state is formed. The dotted line represents that bond breaking and formation occur at the same time. Here you can see that the reaction of 2-iodooctane, this is 2-iodooctane, this is the conformational inversion in SN2 reaction. When the nucleophile attack at the center and the back side, then inversion of configuration occur. When there is inversion, it leads to the racemization. It is rule of thumb, inversion leads to racemization because there is a possibility of nucleophile to attack from the front side and from the back side. In SN2 reaction, the reaction of optically active 2-iodooctane with sodium iodide in SN2 reactions, the reaction of optically active 2-iodooctane with sodium iodide, the reaction becomes reversible and an equilibrium between the two enantiomers leading to racemization. Here you can see in this example, this is the general example. There's here Y is the nucleophile the ability to attack from back side and from the front side. Then there's possibility of formation of racemate. Here this is the example of 2-iodooctane with sodium iodide. Then there is SN1 mechanism. Sometimes during SN1 racemization occur if the rate determining source step is monomolecular formation of a planar with sodium iodide result in the formation of racemate. Then the this OH is conformational inversion other in SN2 reaction. On both sides, the probability of this attack from two sides being equal, racemization may result. This is the slow process, this is the fast, and there is possibility of formation of two equal amount of enantiomer. This is called racemization. In practice, however, some degree of inversion always take place depending on the structure of halide, in particular the relative stability of the carbonium and the solvent, particularly its nucleophilic activity, The more stable is the carbonium and the greater is the proportion of racemization. The more nucleophilic is the solvent, the greater is the proportion of the inversion. This is SN1 reaction, a rate determining step leaving behind a carbonium N and has a planar structure, and so extensive racemization occur. Here this is the example SOCl2 and result in the formation of racemization. Retention of a configuration SN1 mechanism. Here configuration is retented. There is a retention in configuration because configuration is not inverted. Only there is possibility of the nucleophile to attack from either side, result in the formation of a racemate. Mutarotation and asymmetric transformation. A compound with a labile chiral center can undergo configurational changes in solution at equilibrium. If there exists a chiral element in the environment, one or other of the enantiomers would predominate in equilibrium and shows complete racemization known as asymmetric transformation. The change in the optical rotation is known as mutarotation. When there is a change in, this is the best definition of mutarotation. When there is change in optical rotation, then this is known as mutarotation. Mutarotation is an experimental observation, phenomenological in nature, and does not have any mechanical implications. Mutarotation is a experimental observation which don't have any mechanical implication. Sometimes from the mutarotation asymmetric transformation result in racemization, as a compound with a labile chiral center can undergo configurational change in solution at equilibrium. If there exists a chiral element in the environment, one or other of the enantiomers would predominate in equilibrium and shows complete racemization known as asymmetric transformation. The change in the optical rotation is known as mutarotation. Mutarotation is an experimental observation, phenomenological in nature, and does not have any mechanical implication. Mutarotation and fast-order asymmetric transformation. Conformational changes which occur in solution involving a single phase known as fast-order asymmetric transformation. Mutarotation and fast-order asymmetric transformation. Conformational changes which occur in solution involving a single phase. When there is only single phase is known as fast-order asymmetric transformation. Example: all reducing sugar except few ketoses and many of them undergo fast-order asymmetric transformation and exhibit mutarotation. As for example, in glucose, equilibrium water corresponds to 38% of alpha and 62% of beta form. There is a mutarotation is a relationship of between alpha and beta. As for example, in glucose, equilibrium in water corresponds to 38% alpha and 62% of beta. The difference between the two percentage is called mutarotation. This is the existence because sometimes glucose exists in racemization form, racemate form, and this is the mutarotation and fast order asymmetric transformation. Here alpha D glucose, this is trace only, this is beta D glucose. Fast order asymmetric transformation in glucose means if there is a mutarotation, it can exist at equilibrium between alpha D and beta D glucose. Mechanism involves protonation of oxide ring, depolarization of one OH by base followed by ring opening to aldehyde form, its subsequent ring close to original hemiacetal or its epimer by acid catalyst. This is the mechanism which is involved in the formation of alpha or beta D glucose. Mutarotation due to structural changes given with gluconolactone, a solution of which in water established between delta glucono and gamma gluconolactone through the intermediate gluconic acid. This is gamma lactone, this is delta, this is delta lactone, this is gamma lactone, this is trace only, and mutarotation due to saturated changes. Here mutarotation result in the formation of delta and gamma lactone. Then second order asymmetric transformation. In an asymmetric transformation, one of the enantiomer or diasteriomer crosses the phase boundary, comes out of the solution as a crystal or immiscible liquid, known as second order asymmetric transformation. 100% conversion of a racemic mixture into a pure enantiomer. Example: a solution of glucose in ethanol is concentrated. The less soluble alpha form crystallizes first, and after equilibrium only alpha form of glucose is obtained. Crystallization of glucose from pyridine gives beta form only. Now you are using different solvents for the resolution of racemic modification. Means when you are using ethanol, alpha form is crystallized, and when you are using the pyridine, beta form is obtained. And hence it is from this example it is clear that a glucose exists in both alpha and beta form in a racemic mixture. This was all about the understanding of your Racemisation, how it's formed, and what is Mutarotation, and how you can make racemate. This is a simple assignments for you. Give the product of the following assignment reaction. Here you will have to show the stereochemistry of this reaction, and definitely you will get two enantiomers. There is possibility of formation of two enantiomers, and you have to elaborate with the mechanism. This is only for your understanding, that how you have understand the lecture. If you have any question, you can ask me. I am here to give you answer. At this, good luck and Allah Hafiz.